Alright, welcome. In this video I'm going to be working some examples of systems of linear equations, solving those systems with row reductions. It's really like you're getting going in linear algebra and starting to solve some systems of linear equations. Alright, so first we want to write the augmented matrix for the system. Okay, that's a real friendly question. That's going to be 4, 1, 5, negative 9, 10, 21. Okay, but maybe, and if that's all you need, you just feel free to skip forward in the video. But maybe you need some help with your row reduction, and so I'm gonna try to row reduce as many of these things as possible, even if it doesn't ask me to, just to give you something to look at. Okay, so I'm going to use this 1 to clear out that 4. So I'm going to take row 1 and subtract 4 of row 2, and I'll have 0, 1. 5 minus negative 36 is going to be 41. Okay. 10 minus 84 is going to, it feels like negative 74. Maybe this was a mistake. Yeah, it feels like this was a mistake. Maybe I made some sort of arithmetic error. Let me pause real quick. Nope, that's just what happens when you make up numbers in this class. I think this was I grabbed this system from elsewhere. I thought it was from when I taught Algebra 1, but it appears that is not where I got that system from. Okay, so this becomes, 0, 1, and negative 74 over 41, I guess, right? And that will be 1, negative 9, and 21. So if I want to clear out that 9, I'm going to take row 2, and I'm going to add 9 copies of row 1, even if this was a mistake to even go down this road in the first place. I will get this. I'll get negative 74 over 41, and then 21 minus 9 times 74 divided by 41. I don't know if 41 even has any factors. It sure doesn't. None are coming to mind. So I don't know that we could do that. Absent having a factor of 41 up in the numerator already. Yeah, so that's going to be how I would reduce it. You could row swap to get it in reduced echelon form if you really needed to, but for our purposes, we can see that was not a very good system. Okay. Now, secondly, we're going to start with an augmented matrix, and then we are going to write the system. Okay, I think you don't need to see the fact that this is write the system. I'll just write it real quick over here. x1 minus 2x2 plus x3 equals 2. 2x1 plus x2 minus x3 equals 1, and negative 3x1 plus x2 minus 2x3 equals negative 5. That's the system that we're going to solve using row reduction. Okay, so let's see, I'll just scrap that, and I will post-its over here too. That looks like about the right size for some row reduction. And all right, I'm going to use this 1 to clear off the 2 and the negative 3. So I'm going to do row 2 minus 2 copies of row 1 and row 3 plus 3 copies of row 1. Okay, that will get me 2 minus 2 is 0. So I'm not changing the first row yet. Row 2 minus 2 copies of row 1 will be 1 plus 4 is 5. Row 2 minus 2 row 1s is going to be negative 3. Row 2 minus 2 row 1s is negative 3. Okay, then I'm adding down 3 copies of that, adding 3 negative 2s, adding 3, 1 minus 6 is negative 5. Negative 2 plus 3 is 1. And let's see, row 3 plus 3 row 1s, that will also be that. Oh, okay. Well, interesting. Looking at all of this, I feel like x2 is going to have to be 0, but maybe I don't see that yet. All right, what am I going to do? All right, maybe you heard in the video, maybe you heard in class. I'm going to tell you, if I can avoid going into the fraction realm, I'm going to avoid it as long as possible. And it's looking like, oh man, if I divide either of those to induce a leading 1, I'm going to end up with some fractions. Now, division by 5 is not that bad, right? Because you're limited to at most 1 decimal place. Division by 10, also fine. Division by 2, not that bad. Division by 41, that's not going to be good. Okay, but I see a way around it. I'm going to add this down just to kill that and make it a 0. And then maybe I'll be able to just, maybe something good will happen. Okay, and I think that I'll be able to kill that off, use whatever comes back here to kill that. But, I don't know if you can see that yet. Maybe you need a little more experience. So I'm going to take row 3, and I'm going to just add row 2. Okay, so I'll have 1, 0, 0, negative 2, 5, 0, 1, negative 3, negative 2, and then I'll have 1 plus negative 3 is also negative 2. Okay. So I know that this is going to become a 1 and a 1, right? So maybe I can make that happen. We'll see if today this pen will write on top of correction tape. We'll see. Oh, that's just great. Okay. Now, let's see. Now I'm going to take this 1 and get rid of that negative 3 and get rid of that 1 as well. And hopefully, yes, this will be nice. So I'm going to take row 1 minus row 3 and row 2 plus 3 copies of row 3. Nothing's going to change over here. Row 1 minus row 3, that's looking like it's not going to be changing. This will still be a 5. We're not changing row 3. Okay, here. So let's do row 2 first. I'm going to add 3 copies of row 3, so that makes that a 0. And then that'll make this a 0 as well. Okay, then over here, I'm taking row 1 and I'm subtracting row 3, so that will become a 0. And what's happening here? Row 1 minus row 3, that makes a 1 there. Okay, now we are pretty much ready to go. We are going to take row 2 and divide it by 5. And so I'll get 1, and, well, 0 divided by 5, still 0. So I am going to use that 1, so I'll have row 1 plus 2 copies of row 2, but I see because everything else is a 0, there's not going to really be much consequence other than that's going to become a 0. And then I'm going to conclude that the system is going to have solution x1 equals 1, x2 equals 0, x3 equals 1. Or you could say the solution is x is 1, 0, 1. Depends on how you're looking at it. All right. The matrix below is row equivalent to an augmented matrix for a system of equations with infinitely many solutions. Give an algebraic description of the set of solutions to the system. Okay, so it's row equivalent to the augmented matrix for the system, and it looks like it's fully reduced. So I'm going to just kind of cover this up, and I'm going to unpackage this. I've got 4 variables, 3 equations. Okay, so I've got x1 plus 2x2 plus 0x3 plus 1x4. That's equal to negative 1. And then I'll have 1x3 plus 3x4 equaling 4. Okay, and so what I'm going to do is I'm going to say, well, it looks like I can solve for x1 and x3 in terms of x2 and x4, and those are just going to have to be my free variables. Okay, and so what am I going to do? I'm going to just say that gives me x1 equals negative 2x2 minus x4 minus 1. Okay, and x3 equals negative 3x4 plus 4. So the, hold on, okay, yeah. Then, oh yeah, this is going to end up being a plane in 4 space because there's 2 free variables. So you could list it out as x1 is this, x2 is unconstrained, it's going to be whatever it's going to be, x3 is this, and x4 is also unconstrained. So you could say the solution, x is the set of all, or it's the set, the solution set is the set of all x that's equal to negative 2x2 minus x4 minus 1, x2, negative 3x4 plus 4, and x4, where x2 and x4 are pretty much allowed to be whatever they want. Okay? And since I have 2 free variables, I know the type of geometric object that has 2 free variables. It's a plane. It's just that this plane is living in 4-dimensional space. So you might not know what that exactly looks like, but you could have a good idea. Next, we're going to talk about 2 planes in space, right? And that's just, in general, it's a linear system, 2 equations, 3 variables. And how are the planes related when the system has no solution? That would be just like in Algebra 1 when we were graphing 2 lines and figuring out, where they intersected. No solution was when they were parallel. For a plane, again, planes won't intersect when they're parallel. So I'm going to draw myself a little parallelogram, and then I'm going to draw another one over here. It's almost exactly the same, right? And so we can see that those are supposed to be parallel. Yes. Pretty decent. The planes are parallel. How are the planes related when the system has infinitely many solutions? Well, that would be where they run into each other and it's a line. So let me draw that first. All right, honestly, I think my rough draft that I did off to the side was a little better, but we've got ourselves 2 planes. They are intersecting, and they intersect in this line, right? Because they do extend in each direction. Okay, they intersect. And I think, in general, 2 planes are either going to be parallel or they're going to intersect somewhere. And if it's 2 planes, then they're going to have to intersect in a line, which leads me to part C. Is it possible for the system to have a unique solution? No, because if the 2 planes are going to hit each other, the resulting intersection is going to be a line which has an infinite number of points on it. So there won't be one unique solution. We would need a 3rd plane to, give us one spot on this line, And I'm not going to try to draw you 3 planes intersecting at one point. I'm not going to do that. That would take me all day, probably. So, no, it's not possible, but we're not going to have to give a reason for that yet. We'll have reasons to give later on in the course. All right, on the back, the system AX equals B has an augmented matrix that's row equivalent to the matrix below. Give values of P, Q, and R that would guarantee that the system has a unique solution. Okay, so I think, I kind of just made this one up when I was making the homework a few days ago. With this one, I think I typically had made P as 0, and then it was like, okay, Q would need to be like 1, or really anything, right? As long as, I think if P is 0, Q and R can be about whatever they want. Think about that. Yeah. If P is 0, Q and R can be whatever they want. This is going to have a unique solution. So I'm going to say P equals 0, Q equals 1, R equals, maybe I'll say it's 2. Okay. It'd probably be whatever it wants. Because if this is 0 and that's a 1, then in the row reduction steps, what's going to happen is I'm going to use that 1 to clear out this column. Then I'll have 0, 5, 0 number. I'll divide by 5, even if that's unpleasant. And then I'll use that 1 to clear out this 2. And I will be able to get it. I'll be able to get all zeros up here, and that will give me a unique solution. All right, so give an example of non-zero values of P, Q, and R that would guarantee the system is inconsistent. Okay, that's why I put P there, is because in the past I'd ask this type of question maybe on a quiz or something, and people would just say, okay, 0, 0, 0, 1. Okay, but I want you to think a little harder about that. I want you to say, like, what would cause you to get 0, 0, 0, 1 besides just already starting with it? And I'm thinking that if we had 0, 5, 6, 8, and then we subtract it down, that would give you 0, 0, 0, 1. So that's just what I'm looking for. P equals 5, Q equals 6, R is not equal to 7, right? So R equals 8, or 6, or 100, whatever you want. Okay. If you can think of any other values of this, I would be interested to hear them. I'm sure there are, but I'm just that one here. I feel like gives you a little bit of freedom so that you can't just say 2, 3, 5. That wouldn't really do anything for you. Yeah, if you think of any others, let me know because I'm kind of curious. All right, but I'm not curious enough to sit there and like work through all of the possibilities. So give an example of non-zero values of P, Q, and R that would guarantee that the system has infinitely many solutions. Okay, I think if we did 5, 6, 7, then we would subtract down. We'd have a row of all zeros. So that's what I'm going to say. But again, if you think of any others, oh, I've got others. Maybe I'll say -10, -12, and -14. You know, it's like proportional. I guess maybe I could find some others that fit in here by just kind of going proportional. But you know, again, if you got any other solutions, let me know. I'd be curious to hear them. Okay, find the solutions to the system with one stop around the unit circle. This one's a good one from the textbook. I always assign this one. So you might not know what to do with this one. And if that's the case, no big deal. What you're going to do is we're going to say, I'm going to let x1 equal cosine of alpha, and let x2 equal sine of beta. Because if we just consider cosine alpha and sine beta to be static, then we have a linear system. Okay. This is kind of just a hint into ways that you can use linear algebra for, you know, in situations that aren't exactly linear. Yeah, because you might be thinking, not everything in the world is linear, but a lot of things can be expressed using linear systems, like differential equations and all sorts of things that you might not suspect. So I've got 2x1 plus 4x2 equals 3, and 3x1 minus 5x2 equals -1. So we just need to row reduce this thing. And I'm going to have, let's see. Oh man, either way, this is going to be kind of annoying. I think I'm going to just start by dividing this by 2 because then, you know, the worst thing I have is 1.5, and I can live with that. So I'm going to divide it. I'll have 1, 2, 1.5. All right. Then I'm going to subtract down 3 copies of row 1 from row 2. So row 2 minus 3 row 1, row 2 minus 3 row 1, -5 minus 6 is -11, and row 1 minus 3 row 2s. Okay, 3 row 2 would be 4, or row 2 minus 3 row 1. I've been saying that wrong the whole time, I think. 3 of these is 4.5, so 1 minus 4.5 is, or -1 minus 4.5 more is -5.5. And then I have not changed the top row. Okay, so I'm going to divide by -11, and I'm going to get 1, 2, 1.5, 0, 1, 1/2. And maybe, just for convenience, I think I'm going to just call that 0.5. Then I'm going to subtract 2 copies of row 2 from row 1, and I'll have 1, 0, 0, 1. So I know there's going to be a solution. Okay, yeah, this is 0.5, and what's going on up here? Okay, so I subtracted 2 halves, so I'm subtracting 1 from, and so, oh, what do you know? x1 is 0.5 and x2 is 0.5. So that means that cosine of alpha equals 0.5. Okay. That's going to give me alpha equals pi divided by 3, and alpha equals 5 pi divided by 3. I could have sine of beta equals 0.5. Okay, and that's going to be pi over 6 and 5 pi over 6. Those are the solutions to the system that are on the first time around the unit circle. Okay. Find the equation of the parabola that passes through 3 points. This is equivalent to a linear system. I remember when I taught Algebra 2, we solved this problem using a 3x3 system, except we had to solve it by hand. It was really unpleasant. I felt bad for the kids at the time. We might have used technology in my class, though. But, you know, that was like 5 years ago, so it's been a while. What I'm going to do is I'm just going to plug in x and y into this equation, and I'm going to get a 3x3 system in A, B, and C. So I'll have, when I plug in -1, I'll get 6 equals 1a minus b plus c. And then I'll get, when I plug in 1, I'll get 4 equals a plus b plus c. Then when I plug in 2, I'll get 9 equals a times 4 plus 2 times b plus c. And then I'm going to set up to row reduce this thing. And I'm seeing strategically, I don't know if writing the system that you're then going to write a matrix for in the very center of the space you've been allotted to work the problem, I don't know if that's very smart. I don't feel very smart right now. So I'm going to transform this to a matrix, and I'm going to call it 1, 1, 4. -1, 1, 2, and 1, 1, 1 with, what is it, 6, 4, 9. All right, so I'm going to take row 2 minus row 1, row 3 minus 4 row 1s. Okay. So I'm not changing row 1 yet. Row 2 minus row 1, row 2 minus row 1, row 2 minus row 1. Okay, so that's looking like this is going to be a 1, and that's going to be a -1. And down here, I'll have subtracting 4. Subtracting 4 would be like adding 4 in that case. 1 minus 4 is -3. 9 minus 24, really? -15? Okay, yeah, that makes sense. Okay, now don't divide by a 6 quite yet, right? Maybe we can do a little bit of work to keep ourselves in the integer world. So maybe I will add up one of these. Let's see. Yep, still my shot. 1, 0, 1. Nope, not 6. That'll become 5. Because I'm adding a row 2 to row 1. 0, 1, 0, -1. And then I'm going to subtract 6 copies of row 2 from row 3. 6 copies of row 2 from row 3, sure enough. Okay, so row 3 minus 6 row 2s is going to be like adding 6 back, and I'll have -9. Now I can divide by my -3, and I'll get 1, 3. Now I'll subtract this up, and I will get 0, 2. So A equals 2. B equals -1, C equals 3, and my parabola is y equals 2x squared minus x plus 3. The last problem I'm going to be doing in this video is find a cubic polynomial with p of 1 equals 5, p prime of 1 equals 5, p of 2 is 17, and p prime of 2 is 21. Okay, I do have extra practice, but it's just like it's just a row reduction drill. Like, do it over and over again until you feel good. I don't think you need to watch me do that. But if you need more support on your row reduction, I would happily work those problems alongside you in person, but I'm not gonna record it for the video or anything. Okay, maybe I'll be able to write this down in a smart way and not need a separate sheet of paper. So P of X is this, and this does require a bit of calculus. So if you're one of my linear algebra students that's concurrent in my calculus, you know the odds are pretty good that you don't have the power rule yet. So, you know, you might just not be able to do this problem quite yet. But if you came back to it in, I don't know, no more than 2 weeks, you'll be fine here. Okay. So if P of X is this, then P prime of X is equal to B plus 2 times C times X plus 3 times D times X squared. Okay, I'm applying the power rule to it. And P of 1 equals 5. So I'm just going to kind of start writing my equations. 5 equals A plus B. Oh, and C and D. That was generous of them to get me 1 with 1. I'm going to probably do P of 2 equals 17 right here. So it'll be 17 equals A plus 5B. No, okay, I was like, P of 2 equals 17. All right, the 5, I got distracted. P of 2 is 17, so it'll be 2B, 4C, and 8D. I was like, yeah, 125. That's going to be a lot to work with in a matrix for this class without technology. So P prime of 1 equals 5. That'll be 5 equals B plus 2 times C times X is 1, so B plus 2C. That's not the B. B plus 2C, and then what goes in here? So P prime of 1 equals 5, so that'll be plus 3D. All right. And then the last one is 21 equaling P prime of 2, so that'll be B plus 2 times C times X will be 4C. And 3dx squared will be 3 times d times 4. That'll be 12d. All right, so I'm going to write myself my augmented matrix. 1, 1, 0, 0, 1, 2, 1, 1. And I don't know why I froze up there. 1, 4, 2, 4. And 1, 8, 3, 12. Equaling 5, 7, 15, and 21. All right. Now I'm going to, I think right off the bat, I'm going to get rid of this. And I might just say, yeah, 1 minus 1 is 0. 2 minus 1 is 1. Yeah, that's looking pretty convenient. 4 minus 1 is 3, 8 minus 1 is 7, so that'll be 3, 7. And then that will become a 2, because I'm just going to subtract 7 minus 5. So I'm up here, I'm going to take this, and I'm going to use that to clear out, oh, am I though? I think I want to use this one to clear out the rest of them because the 2 is less than the 3 and the 4, and the 3 is less than 7 and 12. Okay, I can deal with one negative number here. I'm going to have negativity up top no matter what I do. So I'm going to actually work with this one as my tool. But if you wanted to use that one or even that one to clear out the entire second column, be my guest. Just you can't use that one because if you tried to use the one in the top, you would end up unclearing this. Okay, and then that's not what we want. So this is going to remain the same. I'm going to have that both be 0, and that one also eventually 0. So I'm going to take row 1 and I'm going to subtract row 3. Okay, so that'll be 1 minus 2 is negative 1, 1 minus 3 is negative 2, 5 minus 15 is negative 10. Okay. Then I'm going to take row 3 and I'm going to subtract, or row 2 and I'm going to subtract row 3. So 1 minus 1 is 0, 3 minus 2 is 1, 7 minus 3 is 4, 2 minus 15 is negative 13. Okay. over here this isn't looking good, but I have faith, right? I got this problem from the textbook also, so I got to assume that the solutions are integers and that there is a good solution. I would be really upset if I found that there was no solution or infinitely many solutions. That would be very, very upsetting, right? So, but I think that there should be a cubic polynomial that fits 2 points, 2 derivatives in general, I think. Okay, anyway, over here I'm not changing this row yet. And then here I'm subtracting row 4 minus row 3, row 4 minus row 3, row 3, row 4 minus row 3. All right. So I think now I'd like to use this one to clear off the rest of that column. Okay. And I'll tell you, like, you know, as far as there will be times where we really need to go to reduced echelon form, fully reduced, whatever. But for us, especially trying to solve the system, I'm okay if I'm discovering the value of C in my second row. That doesn't change my experience. I'm still going to get an answer. Okay. All right. So I added up. So I did row 1 plus row 2. So that'll become a positive 2. And I added 23. Whatever. This is unchanged. It's still in the shot. And I'm going to subtract 2. So I've got to subtract 8. 3 minus 8 is negative 5. Subtract 2. 15 minus 26. Shameful, I know, but I don't want to make an error here. Yeah, okay. And then what did I do here? I subtracted 2 again. So 9 minus 8. That's a little better. That's 1, like that. 6 minus 26 is negative 20. All right. So this is kind of promising. You know, I've got this, and I'm going to really use this to clear out that column, and yeah, that'll be all. I'll be good. This was probably the most, didn't expect it, but this is the most intensive row reduction on the whole homework. So 1 0 0 0. 0 0 1 0 0 1 0 0. I'm going to use that to clear. So that's going to eventually be that. Okay, so what did I do here? I subtracted 2. So if I'm subtracting, so I'm adding 40. So 40 minus 23 is 17. Over here I'm subtracting 4, so I'm really adding 80. Okay. 80 minus 13, that's going to be 67. Okay, up here I'm adding 5, so I'm subtracting 100. Okay. And that's what I've got. Hold on just a second. Yeah, I clearly made a very critical row reduction error somewhere in there. I'm surprised that I ended up still getting integers, though. Yeah, well, so pardon me. I don't know. Looks like I might be experimenting with YouTube's video editing tool here on this video. But, you know, I'm gonna just re-record that solution a different time. And I might just chop this off the end of the video. We'll see. I guess if you're watching this and you're going to know that I did not figure out on YouTube how to correct my errors. But that's going to be all for this video. I don't know where I went wrong here, but obviously I went wrong somewhere because these are just crazy coefficients for a polynomial. But if you know where I went wrong, you can just let me know, I guess. Or if you're just having a problem with this particular item, I will work with you on it in class.